So let's look at the single state, and suppose I'm in 5, what is the solution? Or I'm in 4, what's the solution? And the solution, I just wind up doing the action. I hope that you know the answers, but we just want to write an algorithm to do this. Now, how do I do this? What you're thinking when you are in 5 is you are in your head simulating. If I'm in 5, I can do an action suck or go to the next room. And then when I go to the next room, I can either suck and go to the next room. Right? So, in fact, the simulation that you are doing has a structure. If I am in state S5, okay, and if I do suck, I'll get back to S5. If I go left, I'll get back to S5. If I go right, I will get to S6. So this is the structure of some space, of the connectivity of the state space, looking at it from S5. It's a little graphoid. It's like a small fragment of the graph. So you look at the entire graph, it looks like that. Okay? It's not surprising. It's just a graph. So now finding a path is finding a path in the graph. 310. Data structures. Breadth first search, depth first search. Those are the first 2 ideas we'll start from, and we'll do a lot more than that. Okay? So in essence, finding the solution for intelligent agent, a question of what action should I do, becomes finding a path in the graph and doing the actions on that path. Optimal solution is optimal path in the graph. And the only solutions that you knew for doing graph search is breadth first and depth first before you came to this class, unless you have done some other ideas before. 310 would have taught you about breadth first and depth first. One interesting thing to understand with respect to 310 is in 310, graphs typically are small. In the kind of problems we are talking about, the graphs can be very large. You could have a graph of billion states. And oftentimes doing search on those graphs with basically breadth first search, we'll find out is a dumb idea, because even though it will be optimal, you will never actually be able to, you will not have enough memory most of the time, and you will find that depth first search survives, but it has its own problems. It can go into loops, or it will give inoptimal solutions. Then we'll come up with this idea called iterative deepening depth first search, which has both the advantages of depth first and breadth first, while only having a little more overhead compared to the other. And then we'll go to A-star search, which not only does these type of ideas, but also says when it's in a state, it tries to ask itself, how far am I from the goal state? And if you aren't shell-shocked by this much long time of me talking, you would have said, how do you know how far are you from the goal state? That's what you're trying to figure out. That's what the point of A-star search is. Oftentimes, you may not know the exact distance from here to the goal, but you might know approximate bound on the distance. If it turns out that your bound can be proven to be a lower bound, that means the real distance can never be more than the bound you started from. And if you just add that bound to the distance you travel in the search, which is what A-star search does, then it's guaranteed to be optimal. And if it doesn't make sense to you, imagine that what breadth first search is doing is it's assuming that the distance from where you are to the goal state is 0. That's why it is adding 0. You didn't think it was adding anything, it was actually adding a 0. Okay? So if you think that way, then you will get to this notion of informed search, and figuring out general ways in which you can get lower bounds on the distances from where you are to the state you need to reach is this whole idea of heuristics. That's it. To give you a simple connection to that, imagine I'm trying to get to that guy right at that corner there. Okay? What is the exact distance I have to go there? Well, to do that I have to actually find the optimal distance of going to this route. But if I'm only just finding the lower bound, one lower bound is 0. I'll just assume I'm already there. I'm only supposed to be approximate. 0 is approximate. Okay? But if I want a better distance, I can say as the crow flies. I'm not a crow. I can't fly, I can't do a straight line, but if I were to have a straight line distance to him, that is guaranteed to be a lower bound on the real distance. There is nothing faster than going by straight line to him, nothing shorter than going by straight line to him. Suddenly you found that. Now the question then would be, how did I get this idea? You can say, well, straight line distance really can come by looking at this room. This room is full of all kinds of people and benches. I will abstract this room by removing constraints. I can remove all the benches and people. Then I'll have a room, dash, which is a version of this room with no benches and people. I solve the problem of reaching him in that simpler room. That happens to be just a straight line. And so the solution to an abstract problem, the exact solution to an abstraction of the current problem will wind up being a lower bound on the current problems. If you remember this, you already figured out what A-star search does. For any new problem, all you need to do is figure out what is the abstract version, figure out an abstract version for which you can find the correct solution. Exactly. And now the interesting question winds up being, if you make it too abstract, then the bound would be too loose. If you make it too concrete, the bound would be exact and is close to the real value, but then finding the abstract solution would be just as hard as finding the real solution. So the art of heuristics is to figure out what is the right level of abstraction to solve the problem and use that as the bound to push the search. Okay, that is with respect to single state. Let's go back here. And this is what I do mostly for the rest of the next couple of classes. But before we go there, let's see if I wind up not knowing which state I am in. I'm still in a deterministic world, but I no longer know which state I'm starting from. Do you understand what I'm saying? Okay, so I am blind, I'm actually blind. And so previously I said that sensing doesn't matter, but that's because I told you are starting from state 5, because you knew which state you were in. Once you had to open your eyes to figure out which state you are in, and then you can close your eyes and figure out the solution. But if you had no eyes at all, you can't open them even once. Then the question would be, if I tell you this is your states, your goal is to be in either 7 or 8. And your actions are still deterministic. What happens to the states in which the space in which you do the search? So first, in the beginning, what's the state I am in? I don't know what state I am in. So what state am I in? I'm in one of those 8 states. It's just one of those 8 states. Okay? So instead of states, I will make up this new name, fancy name, called belief states. It has an unfortunate shortening. A belief state is a set of states or a distribution over states. So when I said I didn't know what state I am in, I actually am in a different space where each state in that new space is a belief state, which is a subset of the states in the current world. There are 8 states in the current world. How many different subsets of 8 states can you construct? In general, in this class, if you doubt when I ask a question, you say 2 power. That will most of the time will be right. Okay? If there are 8 states and you have to construct all subsets of the 8 states, the power set size is 2 power the size of the set. Right? So the graph, instead of being a graph on 8 states, is a graph on 2 power 8 states. What is 2 power 8? 2 power 5, 2 power 5, 2 power 6, so 256. Okay? It's a much bigger graph. How does it look? That's how it looks. Just because there are 256 different such states, not all of the 256 states are present here. Why? Because you know which state you are starting from and you know what actions you do. When you do actions, you only get certain subsets, not all subsets. In the worst case, there are actually 256 states, 2 power 8 states, but really it turns out it's lower than that in this case. Okay, now it's a beautiful diagram. If you understand this, you understand what you gain by having eyesight. If you ever wondered what are the blind going through, you're in the same world they are in, what is making their life harder? You realize that when you are kind of sauntering around in the world of 8 graph, they are trying to saunter through a graph of 2 power 56, an exponentially larger graph. To do the same thing you need to do, their problem is exponentially larger. Of course, you can say, give up. It's too big, I don't have to do, but if they want to do it, then they're actually going through much harder space. It's a beautiful quantification of what happens when you lose sensing. Okay, now here is a very interesting thing. In this graph, I am actually doing actions right on the sets of states, and I am reconstructing the new sets. And that's not surprising because the actions are still deterministic. Imagine S1, if I do A, I get to S1 dash. S2, if I do A, I get to S2 dash. Then if I am in state S1, S2, a belief state S1, S2, which means I'm in either S1 or S2, but not both. Okay, and then if I do action A, then I'll get to a belief state S1 dash, S2 dash. Okay, now here is interesting thing is from here to here, the cardinality of the belief state, the size of the belief state didn't change. It doesn't have to be that way all the time. Sometimes with an action you do, you can increase the certainty of the world. So for example, imagine in Tempe some buildings are standing, some are not standing, you don't know which buildings are standing, which are not standing, it's too hard to figure that out, I just bomb Tempe. Then I know exactly what the buildings are doing, they're all dead, people are also dead. I have achieved complete certainty by doing this action, which has humongous uncertainty before this action, but after that, uncertainty went away. Sometimes I can increase the uncertainty. Uncertainty here is the size of the belief state. If the belief state becomes larger, the uncertainty is being spread. If it becomes smaller, the uncertainty is reducing. Okay? So in this case, for example, if I'm in any of these states and I do left, the interesting thing is the new state will only be 4 states large, 4 old states large. Because once you do left, you can never be in the right route. Right? Now, finally, here is the interesting thing. If I am in this world and I have the goal of making sure that both rooms are clean, is it possible to solve it if I still don't have eyesight? Yes. Blind do get along. Not all problems can be solved by them, but they can solve some of the problems. But to solve those problems, they are doing exponentially more work because they've been forced to look at exponential algebra. So in this graph, basically, if it didn't know where it's starting from, it will now search in this much bigger graph, and then it will find a path to either of these states. I mean, actually, so basically it finds is, oh wait, 1 second. No, actually in this case, in fact, you have completely figured out the states are individual here. So it can reach the states. Okay, instead of go left and go right, if in fact you only had go to the next room, this is toggle the switch, right? Then you won't know which room you are in, and yet you can make sure that both rooms are clean. So that would be a case where the final belief state is more than one state, but all those states are both states. Do you understand what I'm saying? So it doesn't have to be the case that when you reach the goal, it's a single state. It just has to be the case that the entire belief state is all both states. If a problem can be solved that way, then you basically are now in the multiple state problem. Each of your states is a multiple state, multiple atomic states, and you are searching in a much larger graph. Okay, and this also has a nice name called the conformant planning. Or, as somebody said, nonsense planning. You're not sensing during time. You don't have to open your eyes. Okay? And then you can also have, so that's, okay. So the other question, of course, is this one makes it look as if all problems can be solved without sensing. But I said that if you have a toggle action, which will which basically only takes you to the next room, but the goal is to make sure that the robot is in the left room, you can never reach the goal state without opening your eyes. So not every problem can be solved without sensing. Okay, and if you have to sense, then you will wind up actually, you have to do a more interesting kind of search called contingency search, where the sensing action splits a state into two different belief states. One belief state becomes two different belief states. I won't go into the details right now. But an example of actions that will require problems where you must do sensing in the middle is things like medicate without killing. Imagine you may or may not be suffering from a particular disease, and there is a medicine that will basically cure you of the disease if you have the disease, and would just leave you alone if you don't have the disease. Then I don't need to check whether you are suffering from the disease or not. I just vaccinate everybody with that medicine. That's conformant planning. If on the other hand, the medicine makes people who don't have the disease sick, so it actually kills them if they don't have the disease. But if they have the disease, it cures it. That actually happens a lot of times in medicine. The medicines that you take can actually kill you if you don't have the problems, because some of them are pretty strong medicines. In that case, you are forced to first check whether the person is suffering from the disease or not. And if they're suffering from the disease, you sense that, then you give that medicine, otherwise you don't give the medicine. So in that kind of a problem, without sensing, you won't actually be able to solve the problem. Okay? And then finally, the last thing that I want to mention is both incomplete and complete initial state. Basically, one is talking about belief states, other is talking about single states. Then there is this notion of unknown state space. I don't even know what happens when I do this action. For some states, I know what happens. So remember I said each action is each deterministic action is an S by S matrix, right? And I basically said there will be zeros and ones. Okay? If the model is complete, it will all be zeros and ones. If it's deterministic action and if the model is complete, it will just be zeros and ones. If the model is incomplete, there will be question marks. So that means nobody ever did that action in that state and they don't know what will happen. In that case, essentially it's an unknown state space problem. So actually then you will wind up having to learn the model as well as use it. And that will get you to reinforcement. Okay? So that's your the problem types. Basically this is a single slide which puts all of them together. So there's a deterministic and accessible, that's a single, if the environment is both deterministic and accessible, you get a single state problem. Deterministic but inaccessible, that means you don't know which state you are in, then you get multiple state problem. If you have a non-deterministic and accessible, it is actually, so you went from deterministic accessible to deterministic inaccessible and you got multiple state. What if you keep accessible and make deterministic non-deterministic? That's MDPs. MDP still search in the space of states, not the sets of states. The thing, so it's a very strange thing that losing eyesight increases the search space size exponentially. Having actions that are uncertain doesn't. Did you guys understand what I just said? If you lose eyesight, if you're in a world with 8 states, if you lose eyesight, you're suddenly now in a world with 2 power 8 states. If you are in a world with 8 states, but your action, which used to be deterministic, now became non-deterministic. That means it can actually, when you try to go left, you sometimes go left, sometimes just stay where you are. It turns out the number of states hasn't increased. Okay? Because accessibility is still there. So you know which state you are in by opening your eyes. The only difference there is in the non-deterministic and accessible case, you no longer come up with a single sequence and say this is the plan, I'll do the first action, second action, third action. Instead, you come up with what is called a policy. Policy maps a state to an action. If you are in this state, do this action. If you are in this other state, do this other action. All of a sudden, this starts looking like condition action rules. Except I computed these condition action rules for my problem myself. Nobody wrote these down. Okay? So when we get to MDPs, we will be computing policies, and policy is a generalization of a sequence of actions. A sequence of actions A1 to AN is essentially saying, I don't really care what state here, I'll do A1 first, and then ignore the next state and do A2, ignore the next state, do A3, etc. That's just a kind of a partial policy. It doesn't tell you what to do in every state. And it turns out that was enough if you are in a deterministic world. If you are in a non-deterministic world, when you do an action, you don't know which state you get into. But since you have eyes, you still know where you got to. That would be MDPs. And of course, I can be mean and say, what happens if you are non-deterministic and inaccessible? That would be, again, you are searching in the state of, this case of belief states. Now, of course, there is also uncertainty. So you now have to compute policy for belief states. Instead of policy going from S to A, the policy should go from BS. If you are in a particular belief state, then do this action. Previously, policy would be of the size of the number of states of the world. Now it will be of the size of the 2 power the number of states of the world. Okay? One last thing, and to actually make life look really, really hard is, imagine you are in non-deterministic world means you don't have distributional information. That means you don't know what state has what probability. Okay? So if you have 8 states, the number of belief states in a non-deterministic, truly non-deterministic world would be 2 power 8 belief states. Suppose I tell you, I'll give you a model which actually lets you know how likely you are going to be in what state. So you no longer just say the set of states, but also the probabilities on each of the states. You have more knowledge, not less. You realize that, right? You have more knowledge now. Okay? So on one hand is deterministic, complete knowledge. Non-deterministic, I don't even know where I am. I'm putting you in the middle. I'm telling you the probability in which you are in each of these states. Good or bad, if I tell you the probability. Do you think it's good or bad? I'm giving you more knowledge. You want it or not?
Yes.
How many states are you going to, how many belief states are going to be there now? How many belief states are going to be there now? So basically, nothing much happened really, right? So there used to be 8 states, no knowledge, it became 2 power 8 states, right? Stochastic knowledge, it will be 8 states plus probabilities. So basically, I just really need 8 real numbers, E1 to P8. They're between 0 and 1, such that when you add them up, it will become 1.6. How many such real number vectors are there? How many such real number vectors are there? Somebody said more. My question is, how many more? Infinite. Does that blow your mind? Do you ever want more knowledge in your life or not anymore? I was telling you that knowledge can be a bad thing, right? I mean, you knew this already, but now I'm telling you that if I were to give you more knowledge about what is the likelihood of each state, now each belief state. So if you have 8 states, 1, 0, 0, 0, 0 is a one different state, 0.3 and 1 by 8 all the way is another different state, 1 by 7 here and everything else connect, equal to 1 by 8, 1 by 8 here, 2 by 8, or 1/4 here and everything else is 6 by 8. That's a different state and so on. There are infinite ways of splitting 1 into partitions of big numbers between 0 and 1. There are number of distributions. Basically, I'm asking what is the number of distributions that on an 8-dimensional random variable. 8 times of it. You think it's good to have this information? Your life has become suddenly extremely bad. You went from 256, you used to be in 8, you went to 256, and then now you got more knowledge and you are in infinity. Is the size of your space of belief states. Is good or bad? Not good. But why do we deal with it? Because if we can use that knowledge, we can improve our performance. Knowing the likelihood of states makes us increase our performance. And so when I can show that you know that knowledge, if you didn't reach the performance I expect of a smart person, I can say, yeah, you're not rational. And that's like bad thing. Okay, and you can, as I said, you can always make your life simple by ignoring the knowledge you've been given. Okay, but by keeping the knowledge, you can actually do you can do much better in terms of the overall performance. Okay, so that should make you wake up and think about what's going on and give you extra knowledge. Okay, so the other thing is, So as I said, if I have a state space of, if I think of factored representation, if I have states which are made up of V variables, V number of variables, states that are made up of V number of variables, then there are 2 power V complete states, and if you lose your eyesight, you will have 2 power V belief states. The so-called 2 power 8 is nothing but 2 power 3. And if you get probabilistic knowledge, it becomes a nice infinity. That's the sizes of the search spaces that you're searching. Okay? Okay. What I'm going to do is sort of orient you towards deterministic environment search, and then we'll continue next week when I come back into basically informed search. Okay. So I'll take the simplest single state problem. Here is a map of Romania, and it turns out that the reason actually I was asking Peter Narvik, who actually wrote the textbook, why Romania? Do you have any Romanian ancestry? Apparently not. He just basically felt people might have some idea about the distances if you use US cities, and he assumed that not enough of you know Romanian cities. Okay, so I am starting from Arad, and I am going to Bucharest, and my actions would be going from Arad to Sibiu, Arad to Zerin, Arad to Timisoara, etc. Those are the actions from each of the states. Okay, now to do basically finding the path in this, basically we'll be finding the optimal path in this graph. As I said earlier, the difference between the 310 graph search and this is the graphs are often implicit. The way, even though I wrote the graph here explicitly, typically the way a search problem is specified is I'll give you the initial state, okay? I'll give you a piece of code called successor generation function, child generator, which takes as its input the current state and gives as its output all the states that will come for each of the actions you take. And then I'll give you one more piece of code called goal test, which takes as its input a state and says yes or no. If I give you those, in fact, if I give you the first and the second, I've given a graph. Right? I have a state and I give you a child generator function, I have implicitly defined a graph. If you ever are silly enough to write the entire graph, it will be too big. The fun in AI is not to have to generate the entire graph while trying to find the optimal solution. Making the whole graph and then finding the solution oftentimes might mean that you will never actually be done with generating the graph, because the graphs can be infinitely large. Imagine a situation, more often than not, there may be infinitely large graphs where the distance from the current state to the goal state is still finite.